I can rewrite 36 as 6 squared. Alright, so 6x then has to equal 6 squared. Alright, and then what you're going to do is, I know this is pretty simplistic to see again, x must be 2, but you'll always then set the x1 is equal. Okay, in this case, it's already kind of done for you. There's no equation to solve. Once you make a common base, set those x1s equal. Okay, so letter B, again, you're always taking the bigger one and making it smaller, because otherwise you'd be adding an element into the problem that wasn't there. So I can rewrite 125 as 5 cubed. Okay, now that the bases are the same, I can just set the x1 is equal, and then solve the one or two step equation. This would be 2. Now, sometimes you're going to have to change both bases to something smaller. You can never base up. You can never make the base bigger, because that means, again, you're making the number bigger, and you can't just change a number. But you can make them smaller, because then you're just rewriting as a different form of itself. So I'm going to rewrite these both as powers of 2. Okay, because 2 can be written as a power of both these. So for the
paper.
yeah, that's the one that I said that whenever there's a star, you're going to want to rewrite.
Oh, okay.
Yeah, so just rewrite that real quick. I had to add it on because I realized it was on the homework and there was none to be found on my lesson, so I had to do a little quick editing. Okay, so I can rewrite 8 as 2 to the 3rd. Now, because there's already something in the exponent, I'm going to have to end up distributing that. So just write it right outside the parentheses like that. Right inside parentheses. And then 2 to what power is 32? Yes, good, to the 5th. So I can rewrite that as 2 to the 5th. And again, there's something already there, so I have to multiply them together. So I'm going to put that right in parentheses. So now that I have the bases equaling, I am going to set those x1s equal, and I'm just going to distribute it at the same time. So be careful to distribute all the way through the parentheses. So we're going to get 6n minus 3 equals 10n plus 25. Don't worry, these ones can get pretty ugly. So you might get an ugly fraction. It's okay. Maybe this one doesn't. So I'm going to get the n's on the right. I'm going to subtract the 25 to the left. Yeah, that one doesn't come out bad. But on the homework, they do come out a little bad. So again, sometimes you are going to have to write them both as something smaller if you can't write one as the other. All right, and then we have some where we're going to need to write it as the reciprocal of the base. So for this problem, because the base is the same, I could really kind of transform either side. But I usually like to do it, if possible, to the one without the x. So how would I write 1/4? First of all, as a power of 4, or the base of 4.
4 to the negative 1.
Yes, it would have to be 4 to the negative 1, because 4 is the base, but the negative 1 is what takes it out of that reciprocal. All right, so now x has to equal negative 1. Letter E, right, I'm going to work the right side and make it into a base of 10. Got first thing I have to do to write it as a reciprocal, I know it's gonna have to be a negative exponent. Alright, so that's what's gonna get me the same base by making it negative, and then what power of 10 is 100?
2.
The second power. Good. So now we have them equaling, so I can just say x has to equal -2. Okay, and then this last one, we just have a little bit more work to do. You always want to solve exponential equations only when the base is isolated, the base to the exponent. So if there's a coefficient or any other constant, you're going to have to cancel that out first. So this is not 8 to this power, right? Remember, 4 is the base. This is just 2 times it. So we can divide by 2. All right, we cannot make that a base of 8. That is not how our exponential functions work. So once I have that isolated, I can write them both as a power of 4, or the right side is a power of 4, I should say. 64 to what power is 4?
3.
Good. Right, and now you can set those exponents equal. Alright, so when you're doing the exponential equations, if you can make one the common base as the other, that's kind of the way that you want to go. But of course, you're going to get problems where you can't make them the same base, right? For letter B, I added in a coefficient here. So just add that coefficient on. All right, so looking at letter A, I can't make 15 into a base of 4, right? So what we're going to do is we're going to take the log of both sides. By doing that, if you remember the power rule with logs, if we had the log of a power, like an exponent, we could bring that exponent to the front as multiplication. So by doing this, we can pull that x and whatever's with it down to the front, and it's no longer in the exponent anymore, we can solve. So here, the base is isolated, so let's take the log of both sides. Remember, it's an equation, so you do have to do the same thing to both sides. Now, what that allows me to do is to use the power rule, which is going to bring this exponent right to the front. So now I'm going to have x times the log of 4 equals the log of 15. Okay, and by picking the common log, that is on your calculator. So once we isolate the x, we'll have an exact answer, and then we can plug it right into our calculator using the log button. Okay, so now to get x alone, I'm just going to divide both sides by log of 4, which is just some decimal. I've got my exact answer, which I do want as part of your answer. Because this is something that would be, say, on the non-calculator portion of, say, your SATs. Right, if they wanted you to solve this, you wouldn't be able to solve it without a calculator, so you would give the exact answer. And let's stay rounding to the nearest 1,000, so 3 digits. What should I do first before I can do anything? Good, divide that 2 out of there. And then try to follow what we just did in the last problem to see if you can take this all the way. take the log of both sides, which will allow us to use the power rule. That whole thing right here is your entire answer done exact, and then we have the approximated with our calculator. So with the next set of examples, we've got E bases. So we are going to skip letter B. So when there's an E, we're still going to isolate, because we want to isolate the E to whatever power it is. But instead of solving by taking logs, we're going to take the natural log. Remember, E and ln go hand in hand. So we're going to isolate, but this, I'm going to show you the property, the reason why it's going to work. So can anyone tell me what that equals? You can put it in your calculator because you do have that stuff in your calculator, or you can convert it. You can put the base in. Yes, excellent. So that actually equals 1. You could convert it like this, right? Put the base in, and you would say, all right, e to what power is e? First power. So because the natural log of e is 1, in this case, when we take it to both sides, we're going to bring the exponent to the front, but it's just going to be multiplied by 1. So it's kind of going to cancel out on that side. Okay, so I'll show you what I mean. So first thing we're going to do with letter A is we're going to divide both sides by 40, so we isolate. Okay, now I've got an E equation, so I don't want to use regular logs because then the base won't go away. So what I want to do is I want to do the natural log. So we'll do the ln of both sides. Yes, thank you. Sorry if you added on a 0 like I did, please take it away. So natural log both sides, because you always have to do the same thing on both sides. Now, as I bring this to the front using the power rule, I would have 0.6x times 1, because this whole thing just equals 1. So we can just bring that to the front and leave it, because the other part is going to cross out. And now, final step, it's just to divide both sides by 0.6. So our exact answer is ln of 6 divided by 0.6. And then let's put that on our calculator. So let's do this next one together because it brings up an important point. So you've noticed that I've been having one of the answers exact, again, because that's the non-calculator answer. So what that means is, we don't want to be approximating anything until the very last step of rounding, because then we've changed the exact answer into something else. So here, if I go to divide both sides by 3, right, and then in my calculator, I would do 76 divided by 3, and it's a decimal. So if you approximated that, it's now suddenly not exact anymore. So if you get a decimal, just go back to what the fraction was. Leave it like that, because then it's exact, and then we only round at the very end. Okay, so feel free putting in your calculator, check, of course. But then if you do get a decimal that you would have to round, you know, if it was like 0.75 done, you could do that, right? Because you wouldn't be approximating. If it was a terminating decimal within 3 decimal places, you could do that. It's just going to be something that keeps going forever that you would have to round off. We want to leave it a fraction. All right, so now I can take the natural log of both sides because e is isolated. That's going to allow me to pull a negative 9.9 to the front. Oh, 9.9x. And then that would just become 1. So I don't need to even write that. And then just one step to solve here, or at least to get our exact answer, and then we'll plug it in. Do you guys get negative 0.326?
Yeah.
All right, so go ahead and just try that last one. It does have an extra step. Remember that if you have a multi-step kind of invert operations that you have to do, always add or subtract first. So you want to add that 8 out before you divide. Does go in evenly, so we can make that a nice clean 23. If you're not getting the same things, you know, the natural log and the regular log will give you a parenthesis. You do have to make sure you close that before you divide by anything. Right? It's giving you a parenthesis that just belongs to the natural log, so you close it out before you press divide. Alright, so those are the three methods. So if you can make it into a same base, that's usually your best bet. If you have an E thing, use ln, and if you don't have an E base, use log. So now we're just going to do just two of these applications. We don't need to do the second one. So I'm going to show you the compound interest, and again, like we're going to be looking for a part of the exponent, so we're going to have to use logs to get that exponent to the front. So this one does get messy. We can put a lot of it in our calculator, so just be really careful on the way, but it does get a little bit ugly. So we're looking at how long, so T is going to be what we're looking for, because that's time. How long will it take an investment of $25,000 to reach $500,000 at 9% annual interest, compounded monthly? I did put the formulas on the graded assignment, even though you'll have them in your notebook. They will be right there, but you would not pick the E one here, because this is not compounded continuously. So you have to pick the one that has the bigger base. So that is this one. Okay, so the P is always your principal. This is your starting amount. So this will be the 25,000. Right? The other side is always the accumulated value. So what happens after all of that interest has been compounded. So 500,000 goes on the left. Okay, and here's our base in the parentheses. So make sure you write that rate as a decimal. So 0.09. What does n equal? 12, very good. And then 12t. Okay, so we're going to do the exact same thing. We don't have a base of e, so we're not going to use natural log. So first what we want to do is we're going to isolate, because this is our base, right? This is the only thing that's being raised. So first thing we want to do is divide both sides by 25,000. Got the base isolated, so now we want to take the log of both sides. Remember, we don't want to do anything necessarily with the parentheses. We'll save that till the end when we're finding our exact amount. Approximate amount. So log of 20 equals log of this big base. That's what allows us to bring that 12t to the front, and then hang on for a second because I want to show you something. 12t comes down because of the power rule. Now, we're used to, at least, you know, most of what we've done here is just dividing by one thing. But I don't know if you remember anything about literal equations. Like, I can actually divide out anything I don't need here. So this is one piece. It's the log of this. Like, you always have to have the log of an expression. So this is one thing that's multiplying this and this. So I need t alone, I can divide everything else out in one step. Okay, because everything's attached by multiplication right here. So I can divide out whatever I need. So I'm gonna divide out 12 log of this thing from both sides. And that will leave me with just t on the right, or even though I'm gonna move it to the left. And then I can put it on my calculator. So 12 log of this thing. Okay, so see, these things all cancel. Again, the log expression, that's all one big piece, right? It comes as a set. So now I have t equals this part that I have on the left. That's our exact answer. And we're looking for the time in years. And just keep it simple, we're gonna round it to the nearest thousand because we've been doing that with everything. So the only thing I would recommend doing when plugging in your calculator, you always would want to close this log, again, because it's just the log of 20. And then after, when you're dividing by something that's a product, 12 times this, I would add your own parentheses right after you divide. Just so you're locking the denominator together. It's a really good habit to get into whenever you're ever using your calculator. If there's more than one term in the bottom or more than one part to an expression, start your own parenthesis right there. So you can plug it in just like this. Yeah, so it's about 33 and a half years, but you can give it just like this. I'm not making you turn anything into months, so I have no problem with just that. Okay, so I'm just going to show you one more example because it has a couple different pieces. It puts everything together from the last 2 days. But again, I know that gets ugly, but if you're just really careful about the steps, you do get to put it on your calculator at the end. So just be careful, and of course, because tomorrow's a grade assignment, just show all your work, and if you show all your work correctly and something goes wrong with the calculator, you'll get almost all the credit. All right, so we're going to go right to this last example. All right, so we've got a function here that gives the number of people infected with measles during an outbreak as here n of t equals this, where n of t is the number of people infected after t days. Okay, so the first question is how many people were infected at the start of the outbreak? Okay, so we want what n of t is, so we're evaluating this expression. What do you think t is at the start of the outbreak?
0.
0. Excellent. Whenever something's at the start of something, that time is always 0 because you haven't started counting yet. Like the time hasn't started yet. So we're going to first evaluate this at n of 0. You can plug that in, but I'm going to explain to you also on another page. Oh my gosh. Now, 0 times anything is 0. So I would be getting 150 e to the 0. Okay, so this can actually be evaluated quite easily without a calculator. Okay, remember that 150 is not the base. This is the coefficient. We're going to multiply that after. What is e to the 0 power equal? 1. Anything to the 0 power is 1, but you have to make sure it's just the base that turns into a 1. All right, that 150 is now 150 times 1, which means there are 150 people that are infected at the start of the outbreak. feel free to plug it in if you want, but you don't have to, as long as you're careful here knowing that that whole thing isn't 1, it's just 150 times 1. All right, next one is how many people are infected after 30 days? So it's still giving us the time here. We're gonna plug in a 30 right here and evaluate. Okay, so we're evaluating n of 30. And then it does say round to the nearest person in this case, so we can just round this one to the nearest person. So you should, I don't want to rush anybody, you should get about 907 people. Now the last one says how many days, so that's your t. So that, because we're clearly looking for t, that's the one we're going to have to use logs. And because this is an e equation, we're going to use the natural log. So it says how many days does it take for the number of infected people to double? Remember that we started with 150 infected people. So what has to go on the other side?
300.
300, excellent. Because we want it to be doubled. Okay, so we rewrite, we fill in that left side, and now t is what we're solving for on the right. Okay, so remember you always want to isolate first. We got to get the e part alone. See out in the open, double, right? That's going to end up doubling the population that are infected. So now we have e alone, natural log both sides. That 0.06t to the front, and then the natural log of e cancels out to 1. And now I just have to divide both sides by 0.06. And I do want you to just make a note of like days or, whatever it's asking for, just so I know that you know what the t is talking about, right? In this case, it's time, and the problem is days. So just make sure you add that. You don't have to write a full complete sentence, but just make sure that you put in the unit or whatever. $11.552, so about 11 and a half days. But again, you can just write it like this to keep it consistent.